we do. It's really exciting. So I did this on Thursday as well. So if you weren't here on Thursday and you go to the Canvas site, there's a link to a YouTube video that is our class. Yeah, it's awesome. So it's like 36 minutes of physics fun. So if you're ever gone, my intention and my goal is to record every day from here on out. So unless, like, I'm obviously not going to record a test day because that would be really quiet, not exciting, right? But any day that we're doing new content, my intention is to record it so that if you're gone, you can hear it. And if you just were like having one of those really not so great days and you need to just like refocus and see it again or see an example again, you can check it out. Does that make sense? That's my goal. I'm going to keep my fingers crossed and try to do that. But if I'm ever off, then let me know. Okay. So yay, technology. All right. So this is the calendar that you have in front of you. So I'm going to do some adjustment. As I told you last time, when I give you a calendar, it's going to be fluid. It's not going to be a static document. So we need to make some notes already. So I'm going to stamp that homework on Friday. So if you already, not Friday, the last day of this week, which is not Friday, it's Tuesday. Tomorrow. Fabuloso. On Tuesday. Was there some Annie going on back there? That's good. So I'm going to stamp this on Tuesday. So if you have it done, good for you. I am going to wait because I don't want to overwhelm people and I want people to actually do it and think about it and understand it. Does that make sense? So I'm going to stamp these two the day that we come back. Does that make sense? So that'll be next Monday. So if you are traveling over Thanksgiving, if you just don't want to have anything to worry about during Thanksgiving, you can work on these tonight. Number 46 from chapter 2 may be a little bit challenging if you try and do it tonight because we're going to do, it's number 45 in the book in class tomorrow. Does that make sense? 45 and 46 are pretty much the same. So this one might be tough, but I think you should be able to do the rest of them. Okay, so I'm going to stamp these two on Monday, the 27th. Oh my goodness, there we go. Does that make sense to everybody? Then we should be back on track and doing okay. Again, this is very loose in terms of how fast and how far and all that sort of thing. I was trying to make sure that we would have time. And the way that it's kind of working out in my head, there's actually, you notice that this is part 1. There will be a part 2 that shows up after this. So this is kind of like the first round, and then we'll do some more deep thinking on it too, okay? Because even though I don't like Isaac Newton, I do think that the laws that are attributed to him are important. So we will spend a little more time than just this. Questions there? We good? Sweet. Okay, so let's jump back into where we were Thursday, last time we were together. Excuse me. We were talking about gravity, right? And I feel like we were like on the brink of something brilliant, and then the bell rang.
Oh, you got something written down because you were talking. Yeah.
Yeah, what did you write down? I don't even remember. I remember it was important.
Yes.
I was remembering that I'm excited, but I kind of got, yeah, and then I forgot to download it, of course, but I'll look for it. I'll describe it for you. Yeah. Gravity on the moon. Talking about mass and weight, right? So there were some things that we wanted to write down. So just to remind ourselves, to get ourselves back in the swing of things, we've been talking about the force of the earth on the object, and then we wanted to define that a little bit more, and we decided that really this thing that I'm insisting that you call the force of the earth on the object is really what you all probably have been for a number of years called gravity, right? The force of gravity. It's a force, it's a push or a pull, but it's a push or a pull of what on an object? What's pushing or pulling? What object is pushing or pulling on these things? The earth is, right? So if I take my puppy and I hold him up here and I let go, he's going to fall. That should not be a surprise to us at this point, correct? That should not be a surprise. The reason that he falls is because he feels a pull, and that's the pull of the earth on the puppy, right? The force of the earth on the puppy, also known as gravity. It's also known as weight, okay? So weight, gravity, and the force of the earth on an object are synonymous. They mean the same thing as long as we're talking about existing on Earth. I suggested that the force of the earth on the object, this was kind of the what are we talking about thing over here. I suggested that this equation is true, okay? And that is really important. The force of the earth, we can find it every single time. We can find the force of the earth on the object if we know the what of the object? The mass of the object, right? If you know the mass of an object, I'm telling you, you can all calculate its weight, the force due to gravity, the force of the earth on that object, because all those three things mean the same thing, right? Okay. One thing that we did talk about was that the mass of the object, unlike the chemists, were right in physics, right? And in physics, we are going to call the mass of the object measured in kilograms always, okay? Even if we're talking about the mass of an electron, the mass of an electron is 9.11, I think, times 10 to the negative 31st kilograms. It's ridiculously small, but we still measure it in kilograms. And we multiply that by our old friend 9.81, okay? The negative just means that the force is pulling which way? Down. Down, because it is, right? It's accelerating down because it's being pulled down. So then we got to the big question, the question that we ended with last time, and that had to do with what? I guess maybe I have my water bottle. I think that's what that is an attempt at a picture of. Yeah. Okay, good. Yes, my pictures are not great. I had my water bottle on Earth. It had a mass of 1 kilogram. My question to you was, what is the mass of my water bottle if I take it to the moon? And the choices were greater than 1 kilogram, 1 kilogram, or less than 1 kilogram. And 0. We'll make it D is 0. Yes. You've had 4 days to stew over this. I know that that's really all you've been thinking about in the last 4 days was what is the mass of Ms. Carveling's water bottle on the moon. So now that you've been thinking about it for 4 days, or maybe you're like, oh, right, yeah, I was supposed to be thinking about that for 4 days. What kind of a conclusion did you come up to? What do you think?
So there is gravity on the moon.
Yeah. Well, that was a question, wasn't it? We had to deal with that. Is there gravity on the moon? Okay, yeah. So let's write that down because that is true. Yes. So is there gravity on the moon? Why, yes, there is. And that's the video I was going to pull up, and I'll see if I can pull it up later in a little bit here. But the answer is yes. Alan Shepard was a astronaut. He did a famous experiment on the moon where he took a feather and a hammer and he dropped them. Okay. If you haven't seen that video, you have seen maybe Neil Armstrong on the moon. Okay. Neil Armstrong, that's what I was doing when the bell rang. I was jumping like Neil, right? I was like, whoa, right? If you've ever seen them, they don't walk like we do on Earth, right? They like leap. So I want you to just think about this. If there was no gravity on the moon, so they land on the moon, they come out and they, walk down the ladder, and then they're standing on the Earth or on the moon, on the surface of the moon. If there's no gravity and he jumps up, where is he going to go? If there's no gravity to pull him down, the net force on him would be what? 0. And see, I'm bringing this right back. This all goes together, ladies and gentlemen. If the net force or the total force on the object is 0, well, I don't know. What else would be pulling on him? Yeah, nothing is what I'm thinking.
When it cancels out.
It can be.
So I'm confused. If there's no, never mind. I was thinking.
Are you with me there? Yeah. So I'm kind of giving you a backwards process, right? Like this, what I'm suggesting to you is not true. But if there was no gravity and he's jumped up, right? There's no force on him, but he's moving this way. If there's no force, tell me about his acceleration. It's going to be 0. And if he has a 0 acceleration, where's he going to go? Same direction he was going, right? At the same speed he was going. Just whoop, bye-bye, see you later. But what actually does happen? Projectile motion, friends. For real, right? When you jump, if you've ever done like a long jump, right? Watch me, I'm not a long jumper, but watch just for a second. Imagine, here we go. Carveling the long jumper. She's not gonna go very far. But if you watch my center of gravity, I go up and I come back. What? Down, up, and I come back down, just like those rockets. Okay, just like anything else. And the reason I come back down is because there's what? Gravity. So is there gravity on the moon? Yes. But if I did the long jump on the moon, how would my distance compare? I'd be able to go farther, right? I could totally win some sort of nothing because everybody else would go further too. Darn it, right? But yes, there is gravity on the moon. It's just that the acceleration due to gravity on the moon is less. Yeah, it's like a quarter of what it is. Okay, so it's a lot smaller. Okay. You haven't answered my question yet, though. You haven't answered my question. So yes, there is gravity on the moon. Tell me, though, what's the mass of my water bottle on the moon? Is it greater than, equal to, less than, or 0? I hear one vote for equal. I hear a couple people said less than. What do you guys think of over there? Make a commitment to something. Do you want to talk for a second? 1 kilogram. On the earth, the mass is 1 kilogram. Talk about it. Talk about it. I want to hear loud physics conversation. No, I think it's this. Like, discuss it. Be bold. I want to know how the mass, I want to know what the mass of my water bottle would be on the moon. If I measured the mass of it.
Mass is what makes it up. You don't get less. Yeah, because we got no other.
We know that.
Yeah, I think you're talking about like atoms. That's it's so weird.
What are you talking about over there?
Mass.
About mass.
Yeah.
Yeah?
It changed. Like you go to like Jupiter and just change it like
Right? Yeah, and Jupiter's kind of a tricky place to talk about because is there a surface of Jupiter? Like you can't really stand on Jupiter. But yes, if you went to the surface, the outer like part of Jupiter that we call Jupiter,
That'd
just be weird. And we're not talking about weird stuff, right? We're just talking about physics. Aiden, what you guys say over there? Equal. Why did you say equal? Because I had to pick something, and so I picked that.
Because the amount.
Yeah, that's exactly it. Mass is just the amount of stuff. So maybe you should have said of stuff, right? Like that's a little like caveat. So maybe but yeah. Mass is amount of stuff. It's the amount of atoms, right? And when I take my water bottle to the moon, unless I've, consumed some water, but let's assume I didn't, because otherwise that's the moot point, right? If I take my water bottle to the moon just like this, did the amount of stuff that makes it up change? No. And that's my mass. So the mass of my water bottle on the moon is still what, friends? 1.0 kilograms. Does that mean everything's the same on the moon? Its weight is different, right? Its weight is different. The force of the moon on the object is not the same as the force of the Earth on the object, okay? So we're going to write this down with some big stars and some big important, like, pay attention to me stuff, right? So the mass of the object doesn't change, but the weight will. Okay. The mass of the object doesn't change, but its weight will, because the weight is just the force of the planet on the object. The mass will be the same. Yeah. Yeah. So another just kind of funny way to look at it, and I mean, sometimes this just kind of helps to solidify it in people's heads. If instead of talking about the water bottle, I talk about me, right? Let me back up for a second. On Earth, when you go to the doctor, they measure your heart rate and they measure your blood pressure and they also measure your weight, right? You step on the scale and they say you weigh so many pounds, okay? Pretty much every other country except for America and Great Britain, if you go to the doctor, they're going to measure your pulse, they're going to measure your blood pressure, and they're also going to measure your what? What do they actually measure? What do they describe it as? Not your BMI. They just talk about it in terms of not pounds, but kilograms. And so really they're asking for they tell you your mass, right? Which is kind of funny because really they use a scale that's been calibrated for the Earth. If they take that to the moon, it's not going to work. Rats. But if they often do, right? Yeah. But I'm just like, kind of conventionally in the US, we talk about pounds. Pounds is a measure of force. Pounds and newtons. So pounds are to newtons. Do you guys like analogies? You love them, right? Pounds are to newtons what inches are to centimeters. Does that make sense? Let me say that again. Pounds are to newtons what inches are to centimeters, okay? It's just a different way to describe it, okay? If I go to the moon, my mass will stay the same, but my weight goes down, right? So like, I'm totally not into like, body shaming, body image issues, but if you think about it that way, right? Like if you want to lose some weight, in big air quotes, right? I want to lose some weight, you just go to the moon and you measure yourself and you're going to have lost a lot of weight. Does that mean that your mass is different? It doesn't. It just means that when you step on that scale, it has a smaller number because it's measuring the force of that, not planet in that case, the moon pulling on you. Does that make sense? Okay. These are things that are, maybe not helpful since they're not very practical, but. Well, yeah, I mean, technically, yes. Because if you step on a scale on the Earth and you weigh 100 pounds, and you go to the moon, you're going to weigh something on the order of what? What did I say? It's like a quarter as much, so like 30 pounds, right? 25, right? Like, right? Does that mean like, so, and this gets into a lot of like other deep things, right? That I don't really want to get into today, but has that changed your body type or anything like that? Absolutely not. It's just changed a number. So really all that weight is a number, right? Yeah, so you don't need to worry about that. Yeah.
Like your weight change and you're like in different mediums. So like if you're in water, like you usually are lighter, right?
So has your mass changed?
No, but I'm talking about like weight because
Yeah.
like gravity and water.
Yeah, so that's a whole nother ball game, right? Because if you draw a picture, so I'm gonna answer that question because it's a super lovely question. So do you remember this picture we drew last time? Where we had the fourth of the floor. I'm gonna do it down here actually, because it'll be more interesting and more relevant to you. So here, let me draw a box. If it's just sitting on the ground with no water, tell me the forces that are acting on it. Gravity, which is really the force of the, because we're gonna be really good kids, right? And then the force of the ground, which way does that one go? Up. Is that okay with everybody? If you want. It's up to you. Okay. Now, if I take that box and instead of just putting it on the ground, I put it in a big tank of water. Okay. Now, not only does the ground push up, but there's also something else that pushes up. Do you know what that is? What else is pushing up on it? That's what it's called. You got it. It's the buoyant force, right? It's the water pushing up on it. Okay. So if you've ever been in the pool with either a little kid, if you're carrying a little kid, my 4-year-old is pretty heavy. She often wants me to carry and really, come on, you're 4, you can walk, right? But if we're in the pool, she doesn't swim yet, so I mean she's learning, but she's not there yet. But I can totally just carry her around for hours on end in the pool because I've got that buoyant force, that water force pushing up. So if I somehow had a fancy scale that I could step on in the pool, it would say less than whatever I weigh. Does that make sense? Yeah, yeah. So you'd have the force of the water. Hello. Where'd it go? Hello. So that's kind of interesting too. Yeah. Yay, buoyancy. It's cool. All right. How are we doing? Okay. That's the force of the earth. That's an easy one to calculate. So I want you to have that in your brain, memorize that, keep that in your brain. I'll even write it up on the board. What? New equation. Force of the earth on an object is equal to the mass of the object times 9.81 meters per second squared. I'm going to put a negative in front of that just so we know that it's always going to go which way? Down. Life is good? Yeah. Sweet. All right. That's an easy force. We're done. Only takes a little while, but that's all right. Now, we've been talking about this ground on the box force, right? The table or the floor or the ground or the whatever, the stool or whatever you want. That has a special name as well, and I want to write that one down. You ready? Here we go. This one people often get confused about, so I want to make sure that we've got it and we've got it figured out. The force of the surface on the object is often referred to as, does anybody know? It starts with an N. That you've heard before? Normal force. So here's the funny thing. Is that the word normal has lots of meanings. In our everyday conversation, normal means regular, plain old, unexciting, right? I'd like the normal mashed potatoes, please, not those crazy ones that Aunt Cecilia made, right? You know what I'm talking about? I just want the regular stuff, okay? Normal in physics and math does not mean regular, plain old, unexciting. Magda's looking really super excited about the word normal because she knows, yeah? Oh, I'm going to make it unconfusing. It's super not confusing. It shouldn't be. It doesn't need to be. Does anybody know what the word normal means in mathematics and physics? No? It doesn't. Bing! You got it. Perpendicular. That's all it means. Yeah, I mean, opposite can go like this too, though, right? Yeah. So normal means perpendicular. So the really nice thing about this force is that the normal force, if you remember that normal means perpendicular, you always know where to draw that arrow because it's always going to be perpendicular to the surface. Easy peasy, right? Always perpendicular. Always, I'm going to say acts perpendicular. You guys okay with that little line thing? Okay, to the surface. Here's something that's kind of annoying or great, depending on how you look at it, about the normal force. The normal force does not have an equation associated with it. So that's nice. We don't have to write anything else down, right? But it does mean that you have to think sometimes. Oh, can't believe I don't want to think. Okay. And the way you can imagine that, this example came to me, I don't know, a couple of years ago, and I think it makes a whole lot of sense, and I hope it makes sense to you. Have you ever been tasked with doing the dishes at your house or helping to do the dishes at your house? Okay. So imagine, if you never had to do that, imagine, try it out, help your family out, but imagine if you were helping somebody else to, after the dishes were dried, either, in the dishwasher or by hand, whatever, you're gonna stack plates on your hands, okay? So if I put, excuse me, right now, am I pushing up at all? Not really, right? If I have this box on my hand, tell me about the net force or the total force acting on this box. 0. How do you know it's 0?
Because the ground or your hand is pushing up and gravity's pulling down and they equal out.
They equal out. And what evidence based on looking at this box can you use? It's not moving, which means that it's not, starts with an A, accelerating, right? I keep going through this every time, and I'm just going to keep doing it because it's good to get it stuck in your head. Box isn't accelerating, so that means the net force is 0. Tell me what forces are acting. Gravity of the earth, right? The earth is pulling down, and my hand, as Maddie said, is pushing up, right? And I know that my hand is pushing up just as much as gravity is pulling down. Life is okay? So if I know the mass of this, then I know the force of gravity, right? And if I know the force of gravity, then I know how much I'm pushing. Life is okay? Okay. Now that doesn't have anything to do with changing or doing the dishes. Now imagine now that your brother or your mom or whoever puts a plate on your hands. Okay. You know that you're pushing up just as much as the earth is pulling down. Then they're going to put another plate. If you don't change the amount of force that you're pushing up with, what's going to happen? Crash, bad news, right? Get out the broom and dustpan, okay? But by nature, because you've been doing this for a long time and because the human body does this, you respond to a plate being put on your hand by pushing up a little bit more. They put another plate on your hand and you push up even more. Are you with me there? They keep stacking plates and you keep pushing up, 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 up. Yeah? Okay? That is this normal force. Okay? That's your body's response. But you don't have to have a brain to do this. If I put a plate on this table, okay, it's going to push up just enough that it needs to, right? I put another plate on, it's going to push up a little bit more. Are you with me? I keep stacking plates. Eventually, even this crazy strong table, if I put plates up to, like I cut a hole in the ceiling and I just keep putting plates on, right? Just keep putting plates on, really heavy plates, like lead plates that are really, really dense, really, really heavy. What's eventually going to happen to this table? It's going to break. Are you with me there? And before it breaks, if you watch really carefully, it's going to bend, right? Okay. That's because you got to go to the atomic level here, the molecular level, right? The atoms are connected with they're connected with bonds that are kind of like little springs, and those springs get stretched ever so slightly, and they get stretched and stretched and stretched. They're only going to stretch as much as they need to push back. Okay. So the normal force doesn't have an equation that goes with it. It's just a force that tries to keep something at rest. Is that making sense? We're going to try some problems with this to kind of get it stuck in our brains because it gets a little bit funny. So let's see here. All right, I've got 3 problems we're going to work through. What time do we get done? Oh, we got a little time. Sweet. All right. For each problem, and this is going to get you in the habit so that we can do these problems with ease as we go through. The first one's pretty straightforward, but I really want you to give it a shot. For each problem, I want you to draw what does FBD mean? Free body diagram. Free body diagram, friendly reminder, is a picture of the object, and only the object, and all of the forces that are acting on that object, right? Okay. And then I stole this from an old thing. So I used to call them F net, but you guys are smart. So we use the little sigma F, okay? We're gonna write the summation equations. Okay, so we're gonna do this together. You might already have started, like, I wanna draw this dog so much. Determine the normal force acting on the dog while he's sitting on a horizontal surface. So we're gonna start by drawing a picture. there's my dog. Maybe I'll give him a little tail and a head because it's fun. Okay. What forces are acting on the dog? The earth is pulling. Which way is it going? Earth is pulling down. I'm going to keep asking that because I think it's really important to keep getting it in your head because it's going to, like, things are going to get interesting in a little bit. Okay. Force of the earth on the dog. Okay. And then what else you got? The force of the ground or the surface or the whatever we want to call it, right? How should those, tell me about the lengths of those arrows. Yeah. Am I going to get out my ruler to check? Probably not, but is it important that they're about the same? It is, yeah. Okay, so there's my free body diagram. It's so cute. And then I'm going to write down my sum of the forces equation. In this case, it's pretty straightforward. There's only one direction, right? In this one, it's going to change, but right now we're okay. So I'm going to write the sum of the forces. I'm going to write it in the y direction just for consistency for later. And now, because I get lazy, like there are some things that I get pretty picky about. Like I really want you to write the force of the earth on the dog and the ground on the dog like this every single time. Okay? But I don't want to have to write that whole thing out every time because that's a big pain. I'm going to put some things in parentheses here. I'm going to remind myself that this is really just the force of gravity, right? That we were talking about before. And I'm going to remind myself that this one, what was this one called? The what kind of force? The normal force. The normal force, the perpendicular force, it's perpendicular to the surface. When you draw a free body diagram, if you want to draw the surface in just to kind of help remind yourself that this force has to be perpendicular to this surface, do it, that's fine. And then I'm going to add those two forces and I'm going to pay attention to the directions that they're pointing because that is really important. The normal force is going up. The gravitational force is going which way? Down. So I'm going to make that a negative. Okay. I know because it says that the dog is just sitting, that the dog is or is not accelerating. It's not accelerating. And if the dog is not accelerating, tell me what I know about the sum of the forces. It's 0. Look at us using Newton's first and second law. Look at that. We're so fancy, right? How you doing? So far, so good? The goal of this problem is to find Fn. Okay. I don't know what Fn is. I just told you there's no equation for it, right? Stink. But I knew to have this one. And I do know that, what? What else do I know? Can I find Fg?
M times K.
You got it. So I'm going to say Fn plus, now this negative sign is really just for the direction, right? This negative sign here is really just for the direction. I only need the direction to be marked one time. You can choose when you want to put it in. So I'm going to say the mass times, I'm going to write it, let's see, what's the best way to, we'll just do it this way, negative 9.81 equals 0. How are we doing? Are we okay? We can plug that mass in. And if I want to get Fn all by itself, I need to move this thing to the other side. Are you with me there? Okay. I'm going to add 0.45 times 9.81 to both sides. So that's going to become positive. Is that good? Because the normal force is pushing which way? Up. So that's a good thing. So Fn is going to be equal to 0.45 kilograms times 9.81 meters per second squared. Y'all can do that multiplication. What's that? 4.41? I don't know. I haven't done it. Is that right? Does that seem reasonable to people?
Why is it a negative?
Why is this negative? So it's negative because this force is pulling down. So I've got a positive plus a negative equals 0. Are you with me there? So I put the negative in here so I wouldn't forget about it. Is that okay so far?
Yeah.
But then, and I kind of talked this through, but I didn't write it down, but I can do that if you want me to. When I move this to the other side, I have to add it, right? Does that make sense? I do the opposite. So, which is good, because I also want this thing to be positive. Because the 4.41 for Fn is up, is positive. Is that okay? Yeah, thank you for asking that. Yeah. How are we doing? Okay? Life is good?
So our final answer would be positive 4.41.
Ding, ding. Yep.
So it would never be negative.
What's it? The normal force? I would say, I don't want to guarantee, it's always scary to guarantee things. I would say unless there's a very strange situation, it won't be negative. Yes. Most of the time it will be positive. Some of the students that I used to teach would then try and like prove me wrong. But you said blah, blah, you know what I'm saying? You're not one of those kids though, I don't think. I think you're more of a trusting soul than, trying to prove me wrong. All right, should we try another one? Ready? Oh, friends, this one's gonna be fun. I don't know if we'll get through this one today, but we'll get it started at least. Oh, I didn't even get a string to take my dog on a walk. I forgot. All right. This is gonna be a good one.
Yeah.
I meant to get a little string. I forgot it. It's in the back. But imagine I'm taking my doggy on a walk, right? I'm walking him like this. Can you imagine that? If I'm taking him on a walk and he's not like sentient, so I'm really just applying a force to a box, right? I'm applying a force that's going up like this at a funny angle. If I'm doing that, that might, or maybe not, affect the normal force. Let's draw a picture and see if we can have a sense of what's going on here. Determine the normal force acting on my doggy who's being walked along a horizontal surface. So I'm going to go ahead and draw myself a horizontal surface. I'm going to draw this funny thing. Oops, 65 degrees relative to the horizontal. So maybe it's going to go up a little bit more like that. Who's ready for some angles? Yeah. Something like that. I'm going to call this an applied force. We haven't talked about that, but that would be like the force of the leash on the dog. Okay. What other forces do I have acting on the dog? Yep, that's actually this one. That's the leash. Yep. So no, you are correct. Yes. So that is my 2.5 Newton force. Absolutely. Are there any other forces acting on the puppy? FG, yep. The force of gravity, right? The force of the earth. I'll put that in parentheses, FG. Anything else acting on the puppy?
Yeah, the force of the ground.
Force of the ground, right? That's what they're asking for. They're asking for the normal force. So let's take a look and let's draw it in. Which way is the normal force going to push? Straight up, perpendicular to the surface, right? Perpendicular, so we're going to draw that like this. Force of the ground on the dog. I'm going to put in parentheses, that's my normal force. And I am going to put in parentheses I'm going to put that as an F sub A. A for applied force. How are we doing? So far, so good? This is kind of a lot to take in, guys, and I know it is. But once we get these kind of process things done, then it'll be easier to approach this kind of stuff. It'll make the lab that we do next week so much better. Okay. We drew a free body diagram. Yay, go us! What was the next thing that it said we should do in order to solve this problem? Do you remember? Equation or equations, right? So we need to write a sum of the forces equation. We're going to add up all the forces that are acting in the y direction. So tell me a force that's acting in the y direction. The ground and the earth. So the ground is my normal force. The ground is, or excuse me, the earth is my gravitational force. I put a negative by that one. Why did I put a negative by that one? To show the direction. It's going down, right? Are there any other forces acting in the up and down direction? This is a little bit tricksy.
The angle thing, the 2.5 newtons.
The angly thing. But that angly thing's acting at an angle. We have to do the components, kind of like we did for that last time when we were doing the SOHCAHTOA business. I'm going to break it up. I'm going to draw a big picture down here so you can see it. Is that okay? Let's see if I can do this. Let me see if I can be clever. Copy. Can I do it? Will it work? Yay! Sweet. Whopping. Fabuloso. Oh, it looks really bad there. It's like really scraggly, but you know, you get it. Add some more space in here. All right. It's up to you. I think it's nice to be able to just see it, but if you know, it's totally your call. I'm not going to look at your notes and say, oh, how come you didn't do that? So 250 newtons acting at 65 degrees. Now, which part do I really care about in this question? This one, the purple or the orange? The purple, the opposite one? Because it's going in the y direction, just like those things, right? Yeah. Yes, ma'am. Oh, yeah. Thank you. Doggy would be going, woo! Yes, thanks for keeping me honest there. There is no normal force because he's flying in the air. Thank you. Yes, it is 2.5. All right. So how am I going to find this purple one? Use what? Sine. Why sine? Opposite and hypotenuse? Let's try it. Let's make sure it makes sense. So the sine of 65 degrees is equal to the opposite. That's this part here. I'm going to call this FA in the y direction. FA in the y direction divided by the hypotenuse, which is FA. How are we doing? Is that okay? Hooray for the trig functions, mostly so that we don't have to just cry and go home. FAY, the part we really care about, is equal to FA, times the sine of 65. Keeping us honest, that's 2.5 times the sine of 65. And pull out those calculators and tell me what that is, because I don't know off the top of my head. I don't have my sine of 65s. 2 point what? 2.265. Do we trust her? Do you agree with her? I don't trust her. Liam, do you agree with her?
Yeah. Do you want to surround it to 2.27?
So I was just thinking that too. You can round it if you want. You don't have to. I mean, like, I'm not going to get any, whatever. Because if you happen to have to do this on like a quiz or something, I would want to see this so that I knew where you got it from. And so I'm not going to get bent out of shape about which one you do. Does that make sense? Mm-hmm. Okay, so let's add that in here. Is that FAY going up or down? Up. So it's going to be a positive. And we assume that if we are dragging this puppy along, is he accelerating in the up or down direction? It's not going through the floor, right? And hopefully he's not flying up off of the thing, as long as it's not 250, right? 250. If it's just 2.5 newtons, probably just doop going along, okay? So that means that there's no acceleration, which means that the forces are going to add up to 0. How are we doing? I know it is. I know it is. You know the force of gravity, though. And you know the FAY. I bet if you put your mind to it, you could figure it out. Did you do it already? No? I want to know that normal force. I bet you can figure it out. What was that? I don't know how to do it. Yeah. I don't know. I want to know what it's going to be. What was FG? 4.41? 4.41 minus 2.265. There you go. I'm so glad to see you guys today. I look forward to seeing you tomorrow. And then it'll be a beautiful, lovely break. We'll wrap up this one tomorrow to remember where we're at.